Hello, Python WebConf. My name is Eli. I'm a developer advocate at Anvil, which is the platform for building full stack web apps with nothing but Python. And I'm here today to talk about modern authentication methods over the web. We're going to be covering three things in this talk: what authentication is and why you might need it, common ways to authenticate your users and their pros and cons, and what makes an authentication system good and how that differs from it simply being secure. So first we have to ask, what is authentication? What is this thing I hear so much about, and why should I care? So let's say that I have built a web service. I'm a Python developer and I've built something and I've put it on the web. Ideally, I have some users, and those users might have things like sensitive data, such as payment information, or they might have access to actions that only they should be able to do, such as posting under a certain identity. And as the person who is writing and maintaining this web app, I'd like to have control over those things. I would like to be able to store their sensitive information securely, and I would like to be able to restrict the actions that they're able to take based on who they are. But ideally, I've not just got the one user. Hopefully, I have lots of users. And authentication is the process of conditionally allowing access to data or actions based on a person's identity. So in a format that we all know and love, the user story, as a web service provider, I would like to verify that somebody is who they say they are, so that I can conditionally allow them to do things and know things based on that identity. So how do we do it? It turns out that identity is actually quite hard to define. What makes me different than somebody else is actually really difficult to pin down, even in person. Over the web, it's even harder. So what we end up doing is we use abstractions instead. So for example, knowledge of a secret password or access to a certain piece of hardware. And we equate these to identity. But these are only ever abstractions. They're only ever approximate, and sometimes they can fail. To take an example of this, let's look at an example that we're all familiar with: usernames and passwords. How this works is that we have a server, where your web app lives. You have your client that then serves that web app to your users, and you have a user. And when a user wants to log in, they will present their credentials, their username and their password, to the client, and the client will then send those away to the server to be verified. The server will verify that the user has presented the correct information and that they are who they say they are for the purposes of this authentication flow. It will then send a message back to the client saying, yep, all is well, and the user is allowed to log in. So this is how it all works in theory, and if everything goes well, it's perfect, right? But here what we're doing is we're assuming that knowledge of the secret password is equivalent to being that person. Because this is a secret, it really matters who knows it. And during that authentication flow, we have three actors, right? We have the user, who obviously has to know the password. That's the assumption on which this whole thing rests. We have the client. We have the client who needs to pass it through, and we have the server who needs to be able to verify it. We have the client and we have the server who needs to be able to verify that the user has presented their correct information. So to start off, we have the user who needs to obviously know their password. And because this is a secret that lives inside the user's head, this has a few implications. Users can forget their password. So if you're using this as your authentication flow for a web app, you need to have some way for users to recover their account in the event that they forget their secret. Users can be tricked into giving away their secret and allowing other people to know it. There's a common type of attack called phishing, which is when one web service will impersonate another in an attempt to trick the user into giving away their credentials to the legitimate service. And this way, other people than the user can know the secret and assume their identity. Obviously, this is bad. It gets worse though, because passwords are things that are stored in a user's head, and a good password is really hard to remember. We'll get onto that later. It can be really tempting for users to reuse a given password. And this means that once a password has been leaked out into the wild to a malicious actor, that malicious actor can then go to other web services that user has accounts with and try that same password. And thereby, if you have one account that's been compromised, perhaps more of your accounts will be compromised. But all of these things we kind of have to live with, right? Because the secret has to live in the user's head. But the server also needs a way to verify that the credentials that the user has supplied are legitimate. How do we do this? Well, it must be able to verify the password. and we'll talk about how it does this, but it also must not allow that password to be discovered. We can't really, like the user certainly can let that password be discovered by, giving it away or reusing it. But certainly you don't want people to be able to get access to your server and then to all of your users' secrets. So the way that we do this is we store records for each user, obviously, with our web app. And one way that you might naively think to do it is you just store their username and password. But then if your account, if your data from your server is leaked, then anybody can just look at this and be able to log in as a user. What we'd like is a way for our server to be able to verify the password's correctness without actually having to store it directly. And there is a way to do this. It's called hash functions. And these are functions that take an input and irreversibly turn it into something else. The idea behind hash functions is that they're hard to programmatically reverse. And the little bit in orange there at the end of that password is something called salt. And it's a bit of random data that we add to the end of a password before we put it into the hash function, just so that it's two passwords that are the same don't end up with the same output string. And there are various reasons that this might be useful in terms of security, but all you really need to know is that it is kind of standard practice when you're storing passwords on the server. And what we end up with instead is on the server, we have this username, we have the user record, and it contains enough information for the server to be able to verify the correctness of a password without having to store that password itself directly in plain text. And this is all well and good, except that actually there are not that many hash functions. And if you have, if your salted hash is leaked, it's still game over. People, if somebody wants to try and brute force guess your password given a salted hash with enough GPU time, they can do that. Except if your password is of a really complicated form that's not very human memorable. And we've got back to the point where these are secrets that have to live in a user's head. And therefore, if you have a really, really complicated one, you're not going to be able to remember very many of them. So this is a really, really common authentication mechanism. And we can see that there are quite a few drawbacks to it. So how do we defend against the vulnerabilities of this authentication system? There's something called multi-factor authentication. And we talked about the abstraction of knowledge of a password being equivalent to identity. This isn't the only kind of abstraction we can use. And here is my my one concession to the title of this talk, my Lord of the Rings meme. We've had one authentication factor, yes, but what about second authentication factor? So authentication factors are ways you can prove who you are. And we might use multiple so that if one thing fails, for example, your password becomes compromised, we can require something else in order to protect against somebody being able to assume your identity. So there are three types of things that are commonly, they generally fall into three groups. Things that you know, like a password, things that you have, like physical access to a phone that can receive texts or has a certain authenticator app on it, and things that you are, like biometrics. And things that you are a little bit complicated in the sense that you can't actually show a web app your fingerprint. What you can do is you can use a fingerprint scanner. And therefore, in order to use this kind of abstraction, we require hardware, and we require to be able to trust that that hardware is doing the correct thing. If you can fool a fingerprint scanner by just showing it a photograph of a fingerprint, that's not very good. And the way that multi-factor authentication works is instead of just requiring one thing, like one password, you require multiple things. So you might require two things that you know, your customer number to log into a bank and a security question, for example. But a problem with this is that if somebody can steal something you know, they can probably steal something else you know using maybe even the same mechanism. But it's not going to be as hard as stealing, for example, something you know and something you have. And for this reason, when we use multi-factor authentication, we usually mix and match between these three types of factors. So, oh, that goes the wrong way around. It is better to use two different things than two things that are the same. And I'm now going to run through a few things that are typically used as second authentication factors. And the first of these is hardware authentication tokens. These are a thing you have. And in order to understand how they work, we're going to need to do a little bit of a primer on public key cryptography. This is it's a mechanism for proving ownership of a secret. So the way that this works is you have a private key and you don't tell this to anyone. This is a secret. You need to keep it absolutely locked down. And to go along with it, you have a public key, and this you share to everybody. And anybody who has the public key can verify that you have the private key when you send them a message and with a signature created using that private key. Anybody who has the public key will be able to look at that, use the public key to say, yes, this was created using the private key, and I know that this person has ownership of that private key, which we're going to consider to be equivalent to identity. And hardware tokens, represented here by a little USB stick with a button on it, are a physical manifestation of that private key. When they're manufactured, they have this baked into them. And this means that you can have a secret that doesn't have to live in your user's head. Here I've represented it with a USB stick, but they can also be built into larger devices like your smartphone and some laptops. And they function pretty much the same. The way that this works in practice is that you have your user, the client, and your server, and the user says, I would like to log in. And the web app goes to the server and says, this person would like to log in. The server comes back and says, well, they've registered with a hardware token. Please ask them to show me that hardware token. And the server, in this message, the server is presenting an authentication challenge, which is a message containing various pieces of data, including the identity of the web service that is making this challenge. All of that data, once the user presents their key, is then passed through to that key. That key does the cryptographic processing required and produces a signed response. The client then passes that all the way back to the server, which is able to use the public key that it has registered to verify that the person's key is, as they've said, it is the correct one. And then it goes back to the client and says, fabulous, let this user log in. And there are certain cool things, aspects of hardware authentication tokens. One is that the device knows about the web service that's making that request. That authentication challenge that was sent from the server contains the information, for example, the URL of the web service. And this provides very strong protection against phishing attacks. Your hardware token is going to be much, much better at spotting typos than you are. In fact, if it hasn't been registered to be work with a certain web service, it won't. So you guard against the type of attack where one web service impersonates another. Another really interesting thing is that the private key never leaves the device itself. All the cryptographic processing is done on that hardware token. So even if your computer that you're plugging it into is riddled with malware, there's no way to actually steal that secret. However, if your computer is riddled with malware, perhaps it might, send lots and lots of false authentication challenges to the key and be able to use these in malicious ways. And for that reason, hardware authentication tokens also require the user's presence. So if you've got one that's a USB stick, something like a YubiKey, it will have a little button on it. And in order to do the cryptographic processing, the user will have to press that button, will have to perform a physical action. And if it's something that's built into a device, something like a smartphone, for example, it will require you to do something like give your fingerprint. However, there are some drawbacks. They can be expensive. If you're going to require these of all the users of your web service, you need to be able to expect that they can all acquire and keep hold of these things. And like with passwords, you need to provide a mechanism for account recovery if this hardware token is lost. It can't be stolen virtually, but it could still be stolen physically, or someone can leave it in the back of a cab. Next thing I'm going to talk about is one-time passwords. And these are kind of similar to the idea of using a hardware token. They also rely on something you have, and that is typically a smartphone. So you can receive one-time passwords, which are, as the name suggests, passwords that are good for one login session, to your phone, either through text message, SMS, or via things like an authentication app. So maybe something that's hooked into your Google account. Google Authenticator is a really common one. And the way that this works in practice is you have your user, you have your web app, its server, and the user has a phone. And the user says, I would like to log in. The web app says, hey, this user wants to log in. Can you send them a one-time password? The server will generate one, send it to the user's phone, and then the user will see that, and they can enter it themselves. And at this point, the client goes back to the server, asks if it's okay, or it's able to verify it itself without needing to go to the server, and the user is logged in. And these are, again, similar to a hardware authentication token in the sense that they rely on you, the user, having something, a physical object, or the ability to receive text messages to a certain phone, but without the hardware outlay of something designed specifically for that purpose. Lots of people have access to text messages, even if they don't have the money to drop on a YubiKey. However, your user might lose their phone. Or somebody might go to their text message carrier and say, oh, I've lost my phone. Can you issue me a new SIM for this same number? And this actually happened in 2018. Reddit suffered a breach because they were using text-based multi-factor authentication. And it's a bit less secure than other methods because it's the ability to receive text to a specific number is actually not necessarily exclusive. Then there's also magic link login. And this is the situation. Slack does this, and it's really cool, where all you need to do is you enter an email. And if you have an account registered to that email, you get an email. And the way that this works in practice is you have your user, your client, your server, and their email provider. And you say, I would like to log in. I'm going to put in my email. And the client goes to the server and says, this user wants to log in. Can you send them an email? The server sends an email with a token in it, so a link including a token that will take you to an authenticated session in the web app when clicked. And this, like a one-time password, is good for one session only. The user clicks that, and they go back to the client, and they are logged in. And this has some advantages over even SMS, even text-based one-time passwords, because if somebody's using a web app, you can be reasonably confident that they have an email address, right? However, as before, if they lose access to that email address, you need to provide some mechanism for account recovery. For example, somebody's signed up to your web service using a student email address and they graduated and their account got closed. This has happened to me. All right, now think about how many online accounts you have and how many of them use password-based authentication. In order to secure all of these accounts, you might want to set up multi-factor authentication. But I know that I have, Facebook, I have my Google account, I've got Tumblr, I've got Twitter, I've got however many different online identities that I have. Now think about, imagine setting up two-factor authentication for all of those. It's a lot. Alternately, think about all the accounts that you use for work. How many accounts an average employee of a tech company has? You've got GitHub, Jira, Slack, any HR systems that you have. Maybe you use Bitbucket, all these different things. Imagine that you run a tech company or you do admin for them. Imagine having to administrate all of those and have multi-factor authentication on all of those. It's a lot of overhead. So it would be really great if we could get the benefits of multi-factor authentication, only having to do it once, but seeing the security implications across multiple accounts. That would be really useful if we only had to, sign in once anywhere. And this is where we get the concept of single sign-on. And the way that this works is you have your web app is a service provider, and then you actually have an identity provided by a different entity, an identity provider. And we use this all the time. For example, if you've ever signed into a web service using your Google account, but it's not a Google web app. Or for example, maybe you work at a bank and you've got some bank supplied credentials and you use those to log into the HR system or something. And the way that this works, the benefits that this provide is that you have one identity provider, centrally managed identity, and you can do things like setting up multi-factor authentication on that one identity. You can change your name, change any details about yourself within that centrally managed identity. You can create new user accounts or remove old user accounts in one place and see the benefits and changes of all of those things across multiple services. So the way that this works sort of mechanically is as follows. You have a user and they want to go to their service provider. For example, let's say that this is GitHub. And they say, I would like to log in to my GitHub account. And GitHub knows that this user has their identity managed by, for example, Google. And so the user is then redirected to the identity provider, a Google server somewhere, with a request to say, this person would like to log in to their GitHub account. And either the user is already in an authenticated session in their browser, in which case we're all good and dandy, fine and dandy, or they have to sign in once. Then this is the single sign-on with whatever authentication mechanism they have previously set up with that identity provider. Once that's happened, the user can be redirected back to the service provider along with some token of proof of identity. And the service provider is able to verify that token of proof. And at which point it goes, yeah, I believe that this user is who the identity provider thinks they are, and I'm going to let them log in. And this is all a little bit vague, and that's because this is really a concept rather than a framework. We're going to talk next about the two main technologies that are used to implement this. But in summary, SSO, single sign-on, is letting you delegate your authentication to a third party. And among the benefits of this, along with centrally managed identity, is that you get to take advantage of that identity provider's security budget, and current authentication data breaches notwithstanding. Usually it's better to rely on a big entity's security budget than your own, particularly for small web service providers. So first, when people had this idea and they were like, let's implement this, they came up, oh, sorry. One last thing, web services don't need to store user credentials. This is great. It means if my GitHub, if GitHub has a breach, I didn't need to store my Google credentials with them. It was all done via redirection. And this means that you protect against the issue where you might think that you're reusing credentials. Isn't this just as bad as using passwords? But it's not the same thing because the authentication is still being managed centrally. Right. Now I'm going to talk about SAML. I was really excited to go and talk about SAML and rant about it because we're about to get into it. So SAML stands for Security Assertion Markup Language, and that is a type of XML. And the way that it works is it implements the authentication flow for single sign-on using XML as the language through which the requests and the token of proof are expressed. And the way that it works is like this. You have your user. They are at their SAML service provider. So for example, the HR system for their employer, and they want to log in, and they are redirected in their browser to the SAML identity provider, along with a request for authentication, which is an XML blob. They're logged in with a SAML identity provider through whatever means they need to do that. And the SAML identity provider then redirects the user in their browser back to the service provider, along with an authentication assertion, which is another blob of XML. And all of these XML messages are signed using public key cryptography, which we talked about earlier. And at this point, the SAML service provider is able to verify that using the public key that it has associated with the identity provider. That's how the SAML service provider verifies this token of proof, is using public key cryptography, and it logs the user in. Now, this is all well and good. And one of the really interesting things about SAML is that actually these two entities, the service provider and the identity provider, never actually communicate directly. It's all done through browser redirects through the user. And one interesting thing that comes out of this is that actually your identity provider doesn't need to be connected to the internet. It can be on a closed and private network that your user has access to. And you can be using credentials managed by that identity provider, that offline identity provider, to authenticate with services that are on the public web. And that's really interesting. For example, let's say you want to have, your identity management for all of your employees in an air-gapped network. You can still do that. However, it does have some downsides. And one of these is the fact that it is, well, because it's based on XML, it kind of has a lot of vulnerabilities baked into it. And we're going to take a look at one particular example of this. Here are two pieces of XML, right? Specifically pieces of SAML. And you can see that they are different. They are different byte strings, but they actually represent the same kind of information, right? They both mean the same thing. However, public key cryptography works over byte strings. And here we have two different byte strings that really ought to be considered to be the same thing. And if you just leave this as is, you're going to end up with mismatches in expectations of the way that the SAML blobs are written between your two entities, perhaps. You're going to leave space for attackers to take advantage of those gaps. So what we would like to do is we would like to have some mechanism that takes these two SAML blobs and says, I know how to understand these. I'm going to consider these two things to be the same. And we can write algorithms to do this, and they are called canonicalization algorithms. And this is great, right? We can do this. However, there are issues that come up with the fact that you need to make sure that both your identity provider and your service provider are using the same canonicalization algorithm, because there are multiple, and you need to make sure that they have both been implemented in the same way. For example, do they both handle XML comments in the same way? If they don't, you're leaving an opportunity for somebody to take advantage of that mismatch. And so for this reason, if SAML had been the only way to do single sign-on across the wider web, we might not have seen it take off in the way that it has. But fortunately, there's another option. OpenID Connect. And this is a very similar thing. If you will recognize, if you recognize a screen like this, you've used it before. So this is when you're using Google to sign into GitHub. That's done over OIDC rather than SAML. And the way that it works is, at first blush, looks quite similar. You have your service provider and an OIDC authentication server, which is what the identity provider is called in OIDC world. And your user would like to log in. They are redirected to a specific endpoint in the authentication server called the authorize endpoint. And at this point, they authorize, they're logged in, and they are sent back or along to their service provider, along with an authorization code. Now, this is not the token of proof of identity. What the service provider does with this is it directly communicates with the authentication server at a different endpoint and says, I was given this authorization code. Can you tell me, can you give me the token of proof of this user having logged in? And the server will do that. It will send back an ID token. And at this point, the service provider can either cryptographically verify that itself and log the user in, or it has the option to send that back to the authentication server to yet another endpoint called the introspection endpoint. And this allows the service provider to delegate not only authentication, but the verification of that token to the authentication server. The authentication server will receive the ID token and say, yeah, I issued that, and that person is who they say they are, you're good to go. And the user can be logged in. And one of the things that this gives you is that the authentication server has at this point the option to revoke access for that specific token. It could say, oh yeah, I did log that person in, but they've since deleted their account, or I did that in error. And this allows an extra layer of security and for the service provider to trust that the ID token is legitimate. There are two main differences between OIDC and SAML, and they are as follows. OIDC uses JSON Web Tokens as its language for expressing requests and tokens rather than XML. And the key difference that really matters here is that JSON Web Tokens do have industry standards for canonicalization and for encoding. And they are also far less flexible in the amount of things that you're allowed to express. So for example, in SAML, you can actually express multiple authentication assertions within a single message. JSON Web Tokens are far more restricted, and therefore the flows that are allowed are far more hardened against attack. And the other thing, as we mentioned, is that token verification can actually be outsourced to the server. It means that if you are a web service, if you're writing a web service, you don't actually have to handle all of that authentication yourself or all of that verification yourself. You can actually just outsource it to the server. And the reasons that these endpoints exist and that there must be an endpoint which you can send tokens to in order to be verified is because OIDC is built on top of another framework called OAuth. You don't really need to know much about it for the purposes of authentication, but it essentially gives you a lot more, it gives you a lot of these mechanisms for free. So we have now taken a tour of all of the ways that you can authenticate your users. And we now need to think about what makes an authentication system good and whether or not this is actually the same thing as it being secure. Obviously, security is a huge part of this, right? If anybody can get hold of my bank details by, just logging into Etsy, that's not good. Security is a must. It's the reason that we do this in the first place. So let's go back to the example of our username and password. If done correctly, this is secure. But by done correctly, we mean that the users have to remember not just one password that looks like this, right? Because anything that's more human readable than this is vulnerable to attack by people who get hold of the salted hash of it. Not just one, but loads of them. This is not user-friendly. You end up using password managers to deal with this problem, but then you also go down the rabbit hole of like, what if that password manager suffers a data breach? What if that password manager ceases to exist, right? This isn't particularly usable. And what you end up with is user behaviors that compromise the security of the entire system, password reuse, for example. So if something is hard to use securely, it's not really secure. You've got to make it easy to take advantage of the security benefits. So now we have two things to consider: security and ease of use. It's easy to think of these two things as being in tension, but actually you just need both. To go back to another example, we have SAML, which I talked about, and the various security implications of using it. However, again, if done correctly, it's very usable for a user. The user doesn't need to remember anything. They just need to, well, they need to be able to authenticate in one place. So it's actually very user-friendly if implemented correctly. And by implemented correctly, I mean that you, as the web developer, have to stay on top of any security breaches that are found in common SAML libraries. You have to make sure that your identity provider and your service provider are in sync with those libraries and are handling the XML requests and assertions safely. And that's a lot to stay on top of. That's a really high overhead. It's hard to implement these things securely. And if it's hard to implement securely, it's not secure. So we now have three things to consider. And it's a lot. There's a lot of overhead in considering how to keep your users safe while making it easy for them to take advantage of that safety and making it not massively painful for you to stay on top of maintaining it. Much like SSO, it would be really great if we could just do the hard thing once and take advantage of it everywhere, right? And that's what we've tried to do at Anvil. I apologize for the smallness of the text on this. This is a screenshot of our users page. And everything that I've talked about in the talk today is a single click to add to your app. These are all of these different things and all of their various security vulnerabilities and things that you need to consider when implementing them safely. You can delegate to a framework that has already taken care of them. If you want to use SAML, far better to have somebody else do the staying on top of the libraries and the vulnerabilities and making sure that it's all handled safely. So at the end of the day, you've got to think about what's going to work for your users and what's going to work for you as developers. And these are some of the problems we have been trying to solve at Anvil. And sort of in summary, it's all about making sure that your things work properly. And that is not only about security, and it's not only about the ease of use for your users, but we're developers. We want to have a pain-free life as well. And it's worth considering that when you build your authentication system. Thank you.